Test. Test. Test.
This section is Spaceballs. Spaceballs?
What right now? Sorry.
Okay.
They're really good.
Yeah, they're impressive.
They honestly don't laugh at it, but literally aside from the data team's reports, they're the best reports I've ever seen.
That's so good.
But
Better line good.
your report was really good. Really good. Your final report. Yes. I still remember it. It was that good.
It's probably all gone.
What year did you
It
take
probably
this?
was.
What year did you take the class?
All 17. But our videos are also the best.
Your video, I still use it.
Yeah.
Even though you slammed me in it.
What did I say?
You said something about grades. I graded too hard.
Oh, yeah. But you get, I still know the lyrics.
Yes.
But you get seems really good then. Yeah.
Did it? No.
Yeah. So it is after that.
And then when you hold up a quiz or something and you put like F minus on it, it's like, really? Did not give you any F minuses.
I guess Steve is still around.
He's still around. Is he teaching? He's teaching.
Or,
And he teaches this in the fall.
really? I haven't seen him since I did that. It's been too long.
I don't even love it.
So confused. I think we could.
I still remember.
We both did on that from all teams, so it or one.
Oh, I think what I decided was
Okay.
but I'm not sure.
Okay. It is like 20 people, so.
Yeah, I think it's a
Or
lot.
16 people, yeah. Okay.
It's like a competition, maybe you up. Fun, don't you can do that. Make the next team queue up.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118
scores are all really low, you just want to
Well, you do great, actually. Keep an eye on that.
I found that too. But you don't get better if you don't get
That's true.
really bad. Without the calendar.
Yeah. So it's got to go in order. It's just this canvas.
Yeah, 2-1 is first. So we're going to start with 2-2. 2-1 is in traffic. In traffic.
I have one of my students with that, they have to do.
Huh?
He's coming from work, he works full time
Okay.
job. So
And which team?
he's the second.
Oh, I think they're all here. They have team shirts on. There's 4 of them, yeah. You can set up. First. Test. Cool. Okay, so the way that we'll do it, you'll have 3 minutes or so to go over your systems, and then we'll just open it up for 2 minutes of questions. And then after you're done, you can wait at the.
Make sure you speak loudly, please.
So this is team 2-2, right?
Good afternoon, welcome. My name is Eva Nortoff, and I'm part of the Marvin Spartans team. On my team with me, I have Chris, Lauren, and Hawker. So we kind of want to give you a brief overview of our whole design, starting with an introduction to our aesthetics. So we already appreciate the character Marvin the Martian, and so we kind of centered our design around him. So we have 3 Marvins holding up the platforms for the rotating arm, which Lauren will get into later. And then on the side panel, we have modeled the Space Jam court. So we have our names on it as well as Martin. And as well, we have laser cut our name into the side of our rotating arm, because we just really wanted to be in the spirit of the competition.
For the driving system, we purchased gears, axles, and wheels because we wanted this system to be the most reliable. Some teams have problems with the wheels slipping on the surface, and since we were driving from point A to point B with the time delay, we couldn't afford to slip at all. And then we also have 3 motors, 3 gears meshed together tightly because for the first sprint and when we were testing it, we had problems with the gears slipping out of place.
So moving on to the arm that Eva mentioned earlier, we have an extending system that allows the arm to start back and then extend out into the forward position that allows us to score the dump shots and the 3 green cups. The way that we did this was we utilized like a Ferris wheel system so that the capsules holding the cups rotate so that they always stay flat. And then when they reach the full extended position, the strings holding the doors on the bottom pull taut and the doors pull out, dropping the balls into the cups. The way that we chose to drive this system is through direct drive motor. And we 3D printed an attachment so that we were able to take the D shape of the motor and convert it to rotational motion of the arm. And for extra support, we added metal cross beams and a hard stop on the ground, which you can see here, that allows the momentum of the arm to be dampened when it does fully extend.
For the jump shot task, we used a catapult design, which the power mechanism for was 2 rat traps. We decided with 2 because initially 1 in previous designs was not enough to allow for sufficient power and adjustability, and was just the bare minimum, so we went with the 2. If you look in the right, or my rightmost side, excuse me, you can see that all the parts are screwed together. This allowed us to take it apart if anything broke, whether it was the rat traps on your arm or the basketball hoop at the top, which is the holder for the balls. On the left 2 photos, you can see the release mechanism. This is a pair of pilot screws, which are held together by a dowel. This dowel is then pulled back by a solenoid, which releases the arm and throws the balls forward at the desired trajectory. Seen there.
Questions? Great. Just a couple questions for me. So, how was your performance in the skier section? What kind of points were you scoring, and what do you expect to score today?
Yeah, so we had, the catapult design was a little less consistent, so we did score 2 in the bucket for one of our runs, but the other runs, we have them in a capsule that actually combined them together, and so you either hit or you didn't, and so we revised that mechanism this time so that the balls were shot in the same trajectory, but they didn't interfere with each other. We had a 3 ball tall container that was the one that was scoring the points for the first round. So we only went for the center cup of the honeycomb. We did all right with that. We did score green 2 out of the 3 runs, like all 3 green. But we wanted to try to push ourselves to get the 3 unique greens for the final competition. As for scoring, the catapult itself is very reliable, and the long arm tends to score 2 out of 3 in the cup, like the desired cups we're going for. Sometimes the side one does tend to bounce out, but it's pretty reliable, so we're excited to do the full run.
Anybody else have a question?
I think you're right at those particular cups.
Like the capsules?
Yeah, so you had 4 points instead of you 3.
Oh, the reason we did those 3 was the 2 wider cups are actually outside of the starting box. And we wanted to limit the amount of complex motions that we could. And so we were like, can we get them positioned in a way that it's a rigid body and we're minimizing movement, essentially. So those 3 we figured out we'd be able to load on without being outside of the starting box. And this box actually has a ramp on the side, so it rolls into the green cup. And this is what allowed us to, we scooted off like an inch, so we were able to stay inside of the starting box.
Okay. All right. Thanks very much.
Thank you.
Thank you. If y'all don't mind waiting over in the lab, that'd be great.
Okay. Not gonna get dip the last page. Sorry, I think I was.
Oh, you're right. Okay.
Thank you.
So we're going to do 3-1 next. your presentation, right?
Yeah.
Okay. All right, so the way we're gonna do it, we'll just give you like 3 minutes to give a little overview, then we'll have a couple minutes of questions, and then after we're done, you can either grab something.
Okay. Sounds good.
Okay, take a look.
All right, hello, my name is Chejin Park, or I go by Jimmy. We are from A3-1. Our team name is KISS, and I'll be introducing the design review. All right, so here's our agenda for today. Just a basic design requirements, jump shot, dunk, and then we'll slightly go over the code. All right, here are just the basic design requirements we kind of based all our decisions off, performing the task, the power sources, and then the dimensions, and of course the cost as well. And then here is the robot that we made. We made it fairly simplistic just to make sure, we found that the more complex it was, the more things that could go wrong with it. So to get the most amount of consistency, we just decided to keep it simple. Right, so first, quick look at the bill of materials. We stay well below the $100 mark, slightly below $50 actually. And the most of our spending was on a tape measure that was used for the dunk task that we're gonna go over in a bit. And pretty much a static product to design the robot.
So now we're going to go into the jump shot functionality of our robot. And for our jump shot, we positioned it on the bottom of our robot in order to create enough space for our tape measure to be on top. So it fits right underneath the platform of the tape measure. So this is a jump shot subassembly component. And everything you see in green here is 3D printed. So we have this adapter inside to actually stick this actuator inside the PVC pipe because we didn't want to directly glue on the actuator. So we made this adapter that fits into the screw holes of the actuator. And how the system works is we feed a ball into here, and we have a ball resting here. As the actuator hits the ball out, the next ball falls down, and the actuator hits it again. And we ended up going with one actuator because in our design sprint 1, we went with 2, but it was actually pretty inconsistent because the 2 valves that we had were slightly different. So one could fly into the bucket, and then one only had enough power to bounce it into the bucket. So that's why we went with 1 to reduce the amount of error that we would have and to make sure that we should try to get it 2 ping pong balls in both buckets.
Right, so for the dunk, this is the dunk overview, just in terms of where it's located in the robot. As Zach said, it's in the top portion of it, and it pretty much comprises of 2 platforms. The forward one is related to supporting the tape measure so that it doesn't dip a lot in the end. And the rear one is where the actuator, the motor, is actually located and has the purpose of protecting and pulling the tape measure out. So the self-assembly itself for the motor, we have a 3D printed spool that has the purpose of guiding the tape measure, retracting and pulling it forward. That is connected directly to the motor, and the motor is just attached to the base frame for the general frame of the robot. So the importance we gave on choosing this design was related to maximizing the stability of it. So we noted that before we were trying to place the tape measure in the front, and that was causing way too much dipping towards the end of it, so the balls wouldn't really reach the cups. So we changed the design and put the jump shot mechanism in the lower end of the robot and pulled it all the way back to the side so that we could have a support platform to reduce the steep.
Lastly, we're going to talk about the code. This is the flowchart of our entire code. Once we study it with the switch status, and then if the switch is pushed, it's going into the main function, activate actuator and extend the measure for dunk task. And then after that, it goes back to the loop, and then everything will be static. That's all about it.
You have any questions?
Thanks. Just one quick one for me. So the jump shot takes 2 shots in succession. Is that how it works?
Yeah, so one ball sits, or we can go back to the jump shot. one ball sits already in the cradle, and then one ball is up here. So as this actuator pushes that first ball out, the next one just falls down into the cradle, and then it hits it again.
Any other questions?
So how many points do you expect to score?
37 per drop. That is 2 hitting inside the gallon tanks with the jump shot, and 3 balls in yellow or the middle green cup from the dunk.
That's cool. Great. Thanks, guys. I think we'll go to the next one. Thank you.
Thank you. Thank you.
Right.
So it's cool if we just go in there.
Yeah, you can go there.
Okay.
That's good. Yeah. So you can do that. You can do that class.
Oh, you can do it all.
You don't really need to take classes. Oh, you don't need to take the classes today. $2-1, right? $2-1, right?
Yes.
Okay. All right, so we're gonna do like 3 minutes of presentation and then a couple minutes of questions. Then after we're done, you can either wait out in the lobby or go to the lab.
Right.
All right, go ahead.
All right, so we are Hunk of Skunks. We are representing our robot Pepe Le Pew Pew, and our members are Sam, I'm Daniel, that's Owen, and that's Kim. So let's begin.
Yep, so this is our jump shot mechanism. It's made up of 4 polished aluminum rods for low friction. This is what the basketballs sit on. Behind the basketballs, you can see here the 2 white strikers that kind of serve to linearize the momentum of the mousetrap arm. So whenever we want to launch the basketballs, we simply activate the solenoid, and that's going to rotate the catch and release the mousetrap arm. And the mousetrap arms will come forward and interact with the strikers, which will push our basketballs forward and outward. And the rails kind of serve to finalize the direction of our basketballs and decrease any variation you would see on impact.
And for the dunk mechanism, when the motor jerks the robot back, leaving a pin holding yours right for an angle, swinging out the wings, and the solenoid and the string to the side will pull the sliding circular bar and force the come out.
For the fabrication of the robot, it's entirely laser cutted. We use MDF, and as you can see on the 2 top images, that our entire jump shot mechanism is laser cutted, and then it's put together by finger joints and glued together. And then the interesting thing about a robot is that it only uses 2 solenoids, 1 motor, a mousetrap, and gravity in order to power it and all its mechanisms. And then for moving the robot, the axle is a threaded rod that we wanted to use a threaded rod because we wanted to find a way that we could fix the gears and the wheels to the axle while it moves. And also we have bearings on the side of our robot to allow the axle to roll freely without any friction.
So overall, in order to get our robot a chance to win, we had 3 things that we wanted to have in mind. We wanted it to be adjustable, we wanted to have the potential to get all of the points, and we wanted to stay within the constraints of the competition. So as you can see in the middle picture, it can reach all 3 green cups, and then the launch mechanism has enough power to get to the bucket. The launch mechanism can rotate up and down to change the angle, and there's notches in our trigger that change the power. And then we can adjust how long our motor rolls to adjust how far the jump mechanism goes out. Now you can see in the picture on the right, it fits within the space, and it only takes 15 seconds to complete. So all of these things give our robot a chance to win.
Any questions?
Great. Just one from me. So you don't use the pneumatics at all, it sounds like.
No, sir.
And what was the, how did you decide to avoid that?
We just wanted to go with a very simple, clear-cut design without, pneumatics would have been more accurate and maybe more adjustable because we could use the pressure, but we also were concerned about the leakages of the tubing and having to deal with compacting that in our design.
Okay, thanks.
I have a question. I don't quite understand how the white arms go out to get into the green cup. I saw in that video somebody standing there shaking it. I don't quite understand how that really works.
Okay, I gotta explain that. So the robot moves backwards right when it gets up, and which kind of pulls it back, and a pin drops out that's holding it back. And so then that's what makes the door slide out. And then the wings start at an angle outwards already. And so then when the door slide hits at the end, then the momentum keeps going and they like rotate outwards.
So did you guys what kind of trouble did you encounter setting that up?
A lot of trouble.
Sometimes the center of gravity would, be changed to the upper front and then it would tip over. Sometimes the pin wouldn't release. We had to work with the motors to make sure that it jerked enough power in order to release the pin. And also, just getting the two arms to fling out correctly sometimes was a trouble.
Cool. Thanks very much.
Thank you.
All right, so y'all can wait here in the lab or on site and we'll call next week.
Are we allowed to test our robot or
We're out over there, so you can.
Thank you.
All right. 3-2. 3-2 or 4-1. Yeah. All right, so 3-2. I think we have 2 more teams, and then we're good. So we're running a little bit behind, right? Just a little bit. 5 minutes. I don't know if I have 4-1. Oh, here's 4-1. All right, so this is team 3-2. All right, so it's just 3. Okay, so we'll have like 15 minutes or so, and then 2 minutes of Q&A. And then after we're done, you can either wait outside or you can wait in the lab. Sounds good. All right, so whenever you're ready.
All right. Hello, I'm Julie Biddlestead.
I'm Brooke Farrow.
I'm Kalia Williams. And our robot is named Extraterrestrial Jelly, which is a reference to Space Jam. And so the customer needs associated with this competition are that we need to score points and not get disqualified. And the way that you score points are you effectively accomplish the jump shot and dunk tasks, which we will talk about a little bit more.
Here is the jump shot task with a slow-mo video where you can see exactly what's going on. Is actually the rubber band the peg's being released and the rubber band actually fires this pin at the balls and it slings through the channel. And the next slide, we talk about how this actually works. There's a pneumatic actuator in the background that fires and pulls the string attached to it, and the peg is pulled up, rubber band is released, and it fires it through the channel. It's on a hinge platform that can be adjusted with height with 2 screws that are not visible. Next slide.
Next, we have the dunk. As you can see, we have 2 tape measures, which is unique to ours compared to other teams that have 1. They are attached to the motor via a motor attachment, and there's also a gate system that is controlled via piston that pulls the rope out to allow 2 balls to deploy at different times. This is our sprint 1 task. As you can see, it is a little unsuccessful because it ends up dropping the balls into the red cup. and not firing only one ball, and that ball misses.
So some of the reasons that we were not successful in Sprint 1 are shown here. So we had a rickety joint that connected the motor to the tape measure, and that made it a little bit inconsistent. We also had a lot of friction between the tape measure and itself, which made it really difficult for it to roll out. It went out super slowly, and it was hard to get it out far enough. And we also didn't have a clear slingshot direction, and so it was a little bit of a guessing game whether or not it would go straight to go in the bucket. So we addressed these flaws for the second sprint, and we have more deliberate 3D printed fasteners. We added some internal lubrication, and so now it glides out as far as we need it to go and even further. And there is a guide channel on the slingshot so that the balls go out straight in the same direction each time. Additionally, we added the gate so that the balls can roll at 2 different times to hit the front center and back center green cups. And we also added multiple tracks to get the ball into the third green cup. And because of these improvements, here's a video of one of our demonstrations to show that we are much better prepared for Sprint 2. And so the measuring gates extend. You can see that as they extend toward their final distance, they sag a little bit, causing the balls to roll down them into the cups. And then if you look really soon, you see that the slingshot launches them. One went in, one bounced off the back rim, but it did hit the back square. And from these instant replays, it's just all over, much more successful and a stronger design. Does anyone have any questions?
Just one from me. Is it fairly repeatable? How do you align where it drops to actual ping pong balls? Kind of like timing, or is it?
The time release, we use delays in the code. So, and then this one is offset by like a couple 100 milliseconds. So it gets farther in the corner.
Thanks. Any other questions?
How's the consistency and repeatability in terms of like scores and scoring averages?
The tape measures became way more consistent when we added WD-40 inside because it used to like create a lot of slack, but now it's very consistent on the distance out. The jump shot is a little less consistent because they move at a higher pace and the rim might cause some issues when it hits the back rim and kind of goes crazy.
I will say, speaking to the slingshot portion, it consistently gets one in the bucket every time. And the reason that the second one doesn't go in actually echoes real basketball, which is because it goes up with a lot of force. And so because it goes at the basket with a lot of force, sometimes it will bounce off the rim as opposed to bouncing into it, the bucket from the back rim.
Great. Thank you very much.
Thank
so
you.
Feel free to wait for whatever outside wherever you want to be, and then we'll start out after the next team.
Sounds good. I appreciate it.
All right, so this is y'all, right? Yeah. All right, so we're gonna do like 3 minutes of presentation and then a couple minutes of questions, and then after that we'll go into your robot. So this is team 4-1, right?
All right, okay. So, hi everyone, we're Team Alley Whoops. I'm Wei.
I'm Taylor.
I'm Jackson. I'm Tim. So this video on the right is going to show us how our robot system works. So for the jump shot, we use a catapult mechanism that can hold and launches the 2 red balls at the same time. And it's powered by pneumatics. For the other side of the robot, for dunking, we use a 2-stage slides plus a rotating arm. And the 2-stage slides is powered by a motor and a string and pulley system. So the dunk mechanism can store all 3 green balls and dunk them into 3 different green cups at the same time. And as you can see in this video, our robot is able to get the maximum score in one single trial. And this is also very consistent that we tested it out earlier this week. It can get maximum score a couple of times in a row.
The dunk mechanism went through 2 major iterations. You can see the first one here on the left. It was basically just a tube attached to a pivot arm. It had several problems, first of which it would occasionally throw the balls out and miss the target. And it was also only capable of placing the dunk balls into a single green cup, which doesn't score the maximum number of points. Our second iteration, which you can see here on the right, is far more aesthetically pleasing, and it consists of 2 pivoting arms that rotate out as the slide simply extends, allowing it to store the green balls into 3 different green cups, which gives it the maximum number of points possible.
So we made our slide mechanism very compact so that we can have more space for the jump shot mechanism and dunk mechanism. This also gives us a really low profile side plate that makes it more aesthetically pleasing. And since we are mainly using MDF boards and laser cutting, it made us really easy to make plug-in structures. And we can use minimal fasteners. And it is really helpful when we are repairing our robot and making prototypes and testing out new designs.
So the compactness that Tim was just talking about can be seen on the right. And then another unique element that we really liked about our design was the stationary base with an extending arm. One thing that we kind of observed with a lot of other groups was that usually the entire robot would move towards the targets, but with the stationary base, we were able to use that almost like an anchor for the extending arm. So that's going to really minimize the error that would be associated with a fully mobile robot. So we really like that design because it's very reliable and it gave us the consistent results that we were looking for. And that's really why we chose this design specifically.
Yeah, thank you.
Thank you.
There's one quick question for me. Why is the bottom of the arm that comes forward curved? Like, what's the functionality of it?
Oh, it's for.
It's to guide them into the cups.
Okay, so as a ping pong ball, I guess we'll see it out there, but as the ping pong comes down, it follows that curve.
Yeah. Also, it kind of prevents the ball from scrolling before it reaches its final state because at its final state, the bottom bar is having a really low angle to let the ball move out really slowly.
Any other questions? Okay, great, thanks. We'll be over in the lab, so you can go and get set up.
Thank you.
All right, so you guys want to get over to the tracks and get them over there?
Is this going to be that next spot? I'm okay. When the first team came in, it was 2-2. That was the first team.
Yeah, I should go in and,
2 times. Because I know you guys won't be here slightly later. I don't know if they're just.
yeah, it's easy. Okay.
Sorry. I don't think that.
Easy enough. All right, so you guys want to get started? I'll just make sure we have it's all the teams.
All right.
For the first one. I'll just make sure we have the next set. Feel free to start them up, get them started. Yeah.
All right. First team is always the three.
The first thing that is
First team always loses.
So I think
That's
those
the way it is.
I thought they did a good job though. I give them high rankings. So I might regret that.
Right.
So we're gonna go to 2, 4. I think that's here. All right, 3, 4. All right, so feel free to set up. I guess this is team 2, 4. About 3 minutes of like presentation and then a couple minutes of questions.
All right.
That's your, yeah, that's your slide.
Which team?
2, 4.
Sorry.
No worries.
Ready to go?
Yep.
All right, let's do it. So welcome to our Mamba design review. So this is John, Jose, me, and Alex. Yeah, I'm Donovan. So yeah, next slide. Yeah, so the aesthetics. So we wanted to focus on a clean, sleek aesthetic design for a robot. So instead of focusing more on the Space Jam theme, we focused on a Kobe Black Mamba theme in tribute of Kobe. So on the design, you can see that we have a snakeskin design, and we also have Mamba lettering. And then we have a snakehead sticker. And on this design, we printed them all out at the Invention Studio, and then we spray painted over them. So yeah, and on to Jose with the jump shot.
So for the jump shot, we basically have 3 components that compose this jump shot. I don't know if you can see it here, but it's also there on the screen. Next slide, more zoomed in. So we have the tube support that basically holds the ball, so then it would be more consistent with the shot that is added with the plate support as seen above as well. And then we have an angle support that would provide a 55-degree angle for the shot that proves to be more consistent through testing, as seen through this figure as well. We calculated and shown that this trajectory has been more consistent with and tested it, and yeah. So moving on, Travis, with the record thing.
So we noticed a limitation in the mechatronics kit for producing linear motion beyond the 6 inches of the actuator's extension. And so our solution to that was a rack and pinion gear, which converts rotational motion into linear motion through the use of a circular gear and a straight toothed rack. The advantages of this is that it gives us a controlled motion that goes at the same speed every time, and with timings of the motors, we know exactly how far it's going to go, and it gives us as much linear motion as we can fit rack in our robot. At the end of it, we have a passive ball release that once our rack and pinion reaches its maximum length over the center green cup, a tension rope pulls a flap outside of the container and drops the ball directly into the milk cup.
Alrighty, so it came down to our final upgrade for our robot. We decided to use wings, which are passively released as we extend our rack and pinion. As it extends, these wings swing out. They hit the 2 outermost cups, which we targeted for the maximum amount of points. And after they're out there, we have an active release with our solenoid at the top, which extends and releases our disc slots and drops the balls into the cups. Any questions?
Just one, is it fairly repeatable, like how it came back? And actually, I was like worried that you were going to go too far.
Yes. So it bounces, but it always lands in the correct position at the end. The wings are angled downwards to assist with the motion.
Okay, so it rests in that position.
Yeah, they rest in that position at the bottom there, and the flaps don't come out until the solenoid pulls them up.
Did you design it where they just go and stop?
Probably, but not in the time frame we have. The limitations with how many different sources of power we had, sort of time constraints and space constraints within our robot, and once we saw that we could consistently make that shot, despite the fact that it bounces, we didn't see a need to tweak it or spend extra time on that with A/B testing and making it perfect.
Sure.
So you put your rack and pinion vertical instead of horizontal. Did you experience any issues with that?
So,
Horizontal.
so through here, the shaft actually goes through, the shaft for this motor actually goes through the bottom of this plate here. And so that provides stabilization for the gear. And since the rack and pinion is on this drawer slide, it's attached in 2 places to different panels.
Oh, it's on the drawer slide.
Yeah. So it's just connected directly to this drawer slide. And as a result, we don't get a lot of loss or anything.
Good job, guys. So feel free to wait outside or in the lobby for you all.
Alrighty.
Thanks. So I think the next one is 3-3. That's- All right, 3-3. So just 3, y'all? Yeah, 3-3, 3. All right. So we're gonna have like 3 minutes of presentation, questions, and then y'all are free to wait in the ideal lab or outside where you're working. So, those are your slide, right?
Yeah.
Okay. All right. So whenever y'all are ready.
All right, hello. We're Team 3, the Martians. I'm Brandon, this is Abdullah, and this is Thomas. We're part of section A03 with Dr. Kalman and Jenny Green. Click the slides. So team overview. So we got our name from Marvin the Martian, one of the original characters of a part of the Looney Tunes universe. And our robot utilizes 5 mouse traps that blast balls into their respective containers. That's why we have the blasters on the machine. And then this is just some images of a machine here. And then puny earthling is like one of the saying, so we added that to the machine as well.
Okay, so how does our machine work? Our machine utilizes 5 mouse traps, 2 for the jump shot and 3 for the dunk. The mouse traps are held back by L brackets that are installed to actuators. Upon activation, the actuators will lift the L brackets, releasing the mouse traps, and the machine is activated by pushing the press button. And that leads us to the following question. What differentiates our machine from the other machines? Simply the exploitation of the mouse traps. We decided to use 5 mouse traps to show you how the effectiveness of this machine that operates by a single, like by a low-cost horsepower.
So since we use most things that were just given to us, and our main cost was just the wood to create a bigger robot to stand so it didn't move as much when our pistons fired off. And yeah, so it was below half our budget. And again, our uniqueness is just using any mouse traps, I believe. I don't think any other team used any, and definitely not 5. Any questions?
How's the power people? Is the kind of where the balls are landing on the dunk pass?
On the dunk, not as reliable as our
25%.
Okay.
For our jump shot, yesterday it was like 1.7 balls per attempt for like 30 trials. So fairly consistent for our.
Any other questions? So it doesn't move on wheels, right? You have wheels there for kind of just like aesthetic.
Yeah.
Okay, great. Good job, guys. All right, so yeah, feel free to wait out in the lab or the hallway there.
Thank you.
Thanks, good job. All right, so the next team is 4-2. All right. Oh. What's that?
More questions?
I was, well, I wasn't me, you, is that what it is?
Yeah.
All right. Because you asked the good questions, Christy. Christy, because you asked the good questions.
You should see my studio, drive me crazy. That's spring break, wasn't it?
Yeah, that's true. You're free?
You told me before.
I did. Yeah, now as soon as I said that, I was like, all right, get it done.
So just a drill, right? Yeah.
Oh, we have to remove the other one. Yeah, let's rotate this.
Right, so this is team 4-2. So you all have about 3 minutes to present, and then a couple minutes of questions.
We first extend the.
Yeah.
Oh, oh. Stop, that's not. Yes, that's fine, I can.
And then the podium there.
Okay, just. Okay, great. All right, let me get the timer out. Good evening, I'm Jared Waters.
And I'm Ben.
We're Team 2, Spaceballs from Section 4. Our robot is designed after the Eagle Flag starship from the movie Spaceballs. And when activated, the wings deploy. It then launches 2 items into target zone 1, and then drives over to target zone 2 and extends the dunk mechanism, which will deposit 3 items in 3 green cups, earning us a total of 44 points, which is what we hope to score in this competition, which is more than the 17, 17, and 12 points we got in the first sprint where we did not do the dunk task. Now for Wyatt for the jump shot mechanism.
Okay, so first the air tank is filled, then when activated, the robot opens the actuator valve, which extends the pneumatic actuator. The catapult arm, which lies in the groove of the actuator adapter, is accelerated by the pneumatic actuator and rotates until it contacts the angle limiting bar, at which point the red stock items are released from the payload bucket and projected towards target zone 1. The catapult is made out of stainless steel plate and tubing. I decided to make a catapult out of metal based on my experience in metal fabrication. Next slide. The metal construction also offers durability, which is important because the catapult arm is impacted by the angle limiting bar and the linear actuator and is less likely to bend or break. It also offers a slimmer compact profile, which is important because it was not designed with a particular final location in mind. And finally, it offers a lower coefficient of friction than wood or plastic, which eliminates the need for bushings. And to talk about the dunk mechanism, here's Nolan.
Thanks, Wyatt. To transfer the item into target zone 2, our robot makes use of a drivetrain and an IR sensor. Once the robot reaches target zone 2, the IR sensor will signal the drivetrain to stop and start the pulley spool motor right there. And it will expand out the drawer slide assembly. And once the drawer slide assembly reaches the end of travel, this limit switch right here will stop the drawer slide from overextending and damaging the robot itself. And to deliver the item into the outer green zones on the target zone, we make use of 2 pivoting arms. They are powered by rubber band right here, and they are kept locked in place by this locking mechanism. One unique point about our dunk mechanism is the use of a cam and follower system. The follower is kept engaged with the cam surface through the use of rubber band right there. And well, because we already use 2 motors and actuator, we must figure out a way to trigger the locking mechanism. And from our testing, we found out that the solenoid is too weak for our need.
So we decided to use a tensioning cable system. It was triggered by when the drawer tire reached the end of travel, the cable will tension and trigger the mechanism and release all the balls.
Any questions?
Just one for me. So as the arm's swinging out, is that just is that propelled forward by a notch track, or what is it?
It's propelled by this rubber band right here.
Oh, okay, nice.
We kept it so it doesn't damage itself. So, yeah.
Any other questions? All right, good job. All right.
Thank you.
Thanks. That was 4-2. So you can wait outside or in there, wherever you want to be.
On both of them.
Yeah. Do we just pick a track?
How are y'all doing it, Jesse?
So,
We just choose a track to.
Yeah, so you guys are gonna be on 4, okay?
All right, 4-3.
we can do that also. Yeah.
Let's try 4.
Yeah.
You guys are
You can do it right.
yeah, if you want to grab it. Right. Yeah. All right, we're pretty close on time. Only like a couple minutes. Feel free to stay over there if you want. This is your slide deck, right?
Yes.
Okay. Yeah. Right, so we'll have like 3 minutes of presentation and then a couple of minutes of questions. And then after you're all done, we'll run your robot.
Okay. Is this just?
Yeah, so it's ready to go.
Alright, awesome.
All right.
All right, guys, we are group 3, total lot domination.
All right, so after repeated testing, we expect for both of our jump shot balls to land in the 5-gallon bucket for a total of 16 points per round. And we expect for one ball, for the dunk task, we expect for one ball to land in the center green cup and 2 other balls to land in either the same green cup or 2 yellow cups for a total of 21 points per round. And that added with the launch task, we expect 38 points per round or 114 points total.
So here in this video, we have this robot here running. It uses a piston-powered catapult, drives over using a motor, and then uses a motor pulley system to extend the drawer slides and then dump the balls into the center green cup. So 2 things that we thought made our design really unique was using a passive string to open our trapdoor. As the drawer slides go out, the string gets taut and pulls the hinge open, allowing the balls to fall out. Additionally, we were able to use most of our ball launcher from the interim design competition in order to launch our catapult, which saved us both time and money in fabricating new parts.
After the interim design competition, we realized that there was a lot of room for improvement with the jump shot task. After we switched to a catapult mechanism from the launching mechanism shown in this video, we were able to increase the number of points scored per round from 3 points to 16 points for this task. Ultimately, the catapult design allowed us to increase the number of balls shot from 1 to 2 and increase the potential to land both of the balls in the 5-gallon bucket as opposed to just hitting the rim with 1. As you can see in the photo of the snapshot from the interim design competition, the second jump shot ball scored 0 points across the board, whereas the first jump shot ball scored a maximum of 3 points across the 3 rounds.
For our bot's reliability, we decided to not incorporate any sensors into our bot due to the drawer system having too many difficulties with that, so we decided to instead use a time sequence. We also had to make a cardboard cutout templates that would help us angle the bot in the starting zone in a way so that we can make consistent distances to the dunk zone. And lastly, for our launch mechanism to have the proper amount of outputs for the buckets, we determined a PSI value of around 45 PSI to set to each time.
Thank you so much.
Just one question for me. So when since it's moving forward and getting to the green cups, it's all putting all the balls in the same cup, right?
Yes.
And how do you align it like in the starting zone? Is it using the template that you got there?
Yeah, so Eric can obviously see it. So in the template, we currently have the pencil marking of where that edge goes on the robot so that we can angle it correctly. So it'll drive and then hit the green cut every time.
Any other questions? Yeah. All right, great, good job. So again, the laboratory, and then we're gonna run the system. So.
Okay.
All right.
Thank you.
Thank you.
Do I need to do anything with this or no?
I can take care of it.
Okay.
That was a 4-3.
That's jumping the gun.
Was that?
That's jumping the gun.
What?
Oh, I was already getting it.
Oh, we're done.
Oh, that was it?
Yeah.
Oh,
That was the last
okay,
one.
no,
Yeah. We're only 7 minutes behind. Not too bad. Oh, it's that team. I think they're not going to be here, so just.
I thought they said there was another team that got perfect place.
So, from at least the number of people,
I believe
they're on 170 people.
I haven't seen anybody get it. Perfect.
They're, I mean, that's long, so it's not actually.
All right.
We good to set this right here? All right.
Wherever you want. You probably want to go over a little bit so you guys can stand there.
Yeah.
Sorry.
No, you're all good. This is the better side anyway. She looks pretty over here.
All right, so it's your slide deck, right?
Yep.
Okay, cool. All right, so we're gonna do, let me just make sure I have everything needed. Okay, we're good. 3 minutes of presentation, a couple minutes of questions, and then after you're done, well, wait over there or wait outside wherever you want.
Okay, awesome. Sounds good. A2 or A25. Yeah. Yep. All right. Is everyone right?
Yep.
All right. Awesome. So we are the Space Shimmies. This is myself, Cole Campbell. And so this is our robot. So we're going to go ahead and start off with the frame itself. We modified the original frame to fit our mechanisms better. So in the first round, we tested out our mechanisms to make sure that they worked, and then we put them all together into one cohesive frame that you see here before you. And so we also splatter painted this with the colors of Space Jam, and use all the available space to best fit our robot.
As far as the jump shot goes, we decided on settling for an air pressure approach rather than the mousetrap, just because we found that with the mousetrap, there was a risk of maybe the spring itself feeling too much strain. And so, as far as testing purposes went, the air pressure way a little bit more consistent. And then the only downside of it is that after we take it out to test it, the air pressure leaks out, so we have to be very precise with that. And then we saw a lot of groups going for like 2 cannons. We decided that one was perfectly fine and just enough, and in all of our tries, it's been pretty successful.
Oh, shoot. There was a video here. We apologize for that. But this was our Sprint 1 prototype, which was in the original frame. And it was showing the jump shot successfully completing from our original frame, where it was off center and all different kinds of things. But the concept of it worked. Here it is. Sorry about that. If it loads. Well, okay.
It's okay.
No worries. Well, that's what it was. For time's sake, we'll go ahead and continue with the dunk.
So the dunk, it originally had the idea of using gravity and the drawer slide to move forward on wheels. We opted to use a regular 2 gears on the motor and strap that down and move it. And the drawer slide mechanism works as dowels holding the balls in place in the holes. And once using the rolling button, which we found out we didn't need to use time, so we use the rolling button to effectively not have to measure any time or distance, just have it stop immediately at the point of the cups. And once the dunk extends, there's a new string on the back of the robot, I don't know if you can see it, that will extend, and it will, by the motion of the dunk of the slide extending, it will pull, and then the balls will drop.
And what started as pins just to hold the balls in place actually ended up becoming rails. So you can kind of see 2 of them sticking out the side here, and that allows us to hit the cups with
higher amount of accuracy because there's more play in where those can hit.
So
rather than simply dropping.
We have a video here on the website. Right?
Yeah, again, sorry about that.
We'll play the videos later.
Okay.
And then for the motion part of it, we use just a simple gear mechanism attached to an axle, motor, gear, axle, and then the wheels. And we, like Alberto said, we use the button mechanism to stop the motion of the gears. Yeah, I believe that is all we have.
How many points are you all expecting to score? Fairly repeatable? Like, what's the?
We are going for the max. So we have this one out the side is going to go, there should in theory, if geometry works, go to the side cup. And then there's two holes. I believe we can extend it out a little bit. So there's a hole like this in the front and a hole in the back that should go into the middle cup and then the back cup. And then we are expecting to shoot 2 balls into the Home Depot bucket. So.
Okay, great. Any questions, Spencer? Yeah, what's your overall cost?
Our overall cost was, I believe, around $70.
And if you got double budget, what would you do?
Honestly, not all that much. The vast majority of this was MDF, which was extremely cheap at Home Depot. And that kind of made it all come together fairly well.
You want to do anything to like improve the accuracy or something or anything like that? Even with double budget?
I'm trying to think if there's, do y'all have anything that y'all would change? Yeah, probably the pneumatic system, making sure that it doesn't leak once you pump it up to a certain amount. But I think that would be just about it. Everything else seems to work fairly well.
Maybe better dowels, because we've had some issues with those.
Yes, one of those broke about 20 minutes ago. So we have had to replace that, but that would be it.
Okay, well, great. Thanks, guys. All right, so next Stephen here. My balls.
But,
oh yeah.
All right, so next one is 3.5.
Thanks.
Let's see. I don't have their presentation. That was 2.5. See if I have 3.5s yet. Just call them in.
All right, 3.5. 3.5. Appropriate robot. Yeah.
Did we change our name on here?
You sent me. Which one was it? This one?
Keith Gibson is our director. Yeah, the title might be outdated then because the email that came out today.
It's okay.
Yeah. We got team name to be something different. Yeah. All right.
How do you put this in presentation view?
Page view, maybe?
Yeah, good way. Is that?
Or I'd say try page view and then it'll let it or a single page.
I'll just do it like.
And then I can.
Do you need to open it in PDF? Is that would be better? In Reader?
Yeah, it might be. Okay. Sorry.
Of course. So 3 minutes of presentation, a couple minutes of questions, and then after y'all are done, you can. What? It needs me to sign in. So
hey, you want to wind it up real quick?
Right now?
Do that. Yeah, just put that sleeve on. Okay. Just so we have it like how can we? Yeah. And then.
Oh my gosh. Like, do I really need to sign in to?
Team 5, our, 3.
Thank you.
And just one thing about our name is that I think our email name changed because of the email that came out, but this was done before that. So that's why this name is different, because we didn't know it actually had to be Space Jam themed. We just thought that was like the theme of the like competition and then.
Yeah, it doesn't have to be.
Oh, okay, I thought our names did have to be, so we sent that email by correcting it. All right, well then we'll go with this name, because I like this a little better.
Log in to use Adobe PDF reader.
I'm sorry, making such an ass out of it.
Oh, no, you're
Yeah.
fine. PDF is supposed to be the language, all of the, how do you put this in I've never put this in full screen mode. Oh, here we go. Okay.
Will one of you guys be giving us the time, or should we keep it ourselves?
Alright,
Yeah, I'll just put this here.
if you end up going the rest of the audience. Alright, so 2, 3, 5.
Alright, and then just start when we start?
Yep.
Alright.
The slides over there for if you want to.
Get start. You want to start?
No, what?
You want to start?
I can do that.
Alright, you're on. Alright, so, okay, routine 5, we'll ratchet and clank because our bot is kind of ratchet. It's just kind of, you know, a lot of quick fixes back there. They're all effective though. So our agenda is problem and constraints, system designs, operations, fabrication, bill of material, and performance. So the problem and constraints you're all probably familiar with, so I'll just go briefly. 4 foot to the middle of that, jump shot, shoot it in, 4 foot to that, dunk, and then 20 by 20 by 18. And then,
All right, so this is the overall design for the test. First of all, we're going to do the shooting and utilize a pneumatic system for that. And second is the movement. It will, so the wheel system will push the robot near to the cuff for the dunk. And the dunk, we utilize a telescopic slide and a dip on the disc and the blade on top.
Right, so getting into the shooting portion, this is a pretty simple setup. We have the tank connected to the valve, and then the valve is split with this joint into the 2 actuators, which are aimed at the button. And so we also have a stopper for the valves because we found that it needs to not be in contact with the ball the entire time with the actuator is accelerating, so to get it the farthest.
For movement, we have a gear reduction system, so it starts at a 25 and then goes down to a 17, so that we rotate the wheel slightly faster than the RPM allows for the motor. And it's a rear wheel drive, and it just pushes it towards the cup within range, so we can put this in the middle of the 3 greens.
And there's a little more detail for the telescopic slide. As you can see, it has 4 slides, and between each, there's a door slide installed, and each slide has pulleys and the pins at the end, so that the motor can't see it, but it will rewind the wire that's connected top of the slide pin right there. So as it rotates, it will wind the wire, and it will push the slide to the front up forward as extension.
And then at the very end, this will be taut, and then it will pull this, twist it, dropping the balls to the holes into the cups.
So it's just simply, like, it's only a tension on that forward side. That way it folds. So they're over there.
For the fabrication, the body is made of MDF, the gears are laser cut. The pulleys are bought and modified, although some of them are 3D printed. Fishing line was used for tight tensile strength, so it wouldn't rip when the gear was pulling it. The MDF board is used for a rotating plane to minimize the weight. The center is cut out, and then weight added at the front to balance.
And here is the bill of material. Most parts of a robot are made of the MDF wood, which totally costs about $18. And the most expensive part of a robot is the 3 slides we bought from Amazon, which costs totally about $20. And the total cost of our robot is about $52.
And there's images of the pneumatic system for the shooting. As you can see, we put 2 actuators on top, and picture of the extension and the wheel.
Question?
Just a question for me. So the shoelace repair cord, how does that work? Is it pulling?
So, yeah, so I don't think it's, when this is fully extended,
Oh, it's
it tends, yeah.
got it. And it causes it to rotate.
Right, and then, so we will initially set it up like this, and then when it's in tension, it gets stopped on top.
It's pretty repeatable, like.
Yeah, it's pretty repeatable. It's a big length.
Other questions?
you help me understand why you have like three boxes there? Anybody understand?
Where exactly are you?
The slides and the three slides that go out. There's like boxes.
Are you talking about this or? Sorry, yeah. Just like.
Oh, the blocks of wood.
Yeah, the
Okay.
blocks of the woods are the parts that slide out on top of.
So why did you use blocks of wood like that?
So we needed to keep it high enough so that when the moment wouldn't deform it to hit the cups, the solo cups, because then that would obviously disqualify us, and we don't want that. So we found blocks of wood about an inch up, and they don't deform as much as like other things. Like MDF's a little more flimsy. It's lighter weight, but
it was hard to find something like with low density that wouldn't deform or bend.
Thank you.
Great. Good job, guys. All right, so you can wait in there or wait outside where we will leave.
Okay, thank you.
Thank you.
That
was a brief one, yeah.
You want to take it? No, all the time. I think put it together. Just so we don't have to keep moving it around. Leave the map?
I think I jumped the gun, so yeah, it's 3-4 now. 3-4. Is your slide deck right?
Yes.
Kind of speed up, it's like been raining, so, yeah, with that. Hey, you can set it there. If you want to put your robot up there, you want to do what you want to do. Okay. You want to do that. All right, so about 3 minutes presentation, then a couple minutes questions, and then free to wait in there or wait outside. Okay, perfect. That's, yeah, you can, okay, all right, I'm there. Let's, all right, is everyone ready? Yep.
All right. Well, thank you all for being here. We're really excited to participate in this and get to see how our robot does. Our team name is Shooting Star, just to kind of line up with the space theme. My name is Adam Nichols. I'm here with my teammates Brian Rowe, Daniel Palladino, and Jordan Carter. All right, so this PowerPoint is pretty driven by the customer requirements of the project. So we're going to touch on, all the major components that we use to accomplish all the customer requirements, including high scoring, maintaining qualification, and being reliable and durable. Here's a quick overview, just to see the side panels. We have them painted to kind of match the Space Jam theme, and then as well as some dimensions to show that we're inside those qualifications and some major components that we're going to get into a little bit later.
All right, our jump shot feature utilizes the pneumatic tank system. And our system has two strengths, which is easy to manufacture and adjustability. And as you can see, it is all on laser threaded, which is like very time efficient. And it is very easy to adjust because as you can see, there are many holes in the side mount, and you can adjust the angle, as well as you can increase or decrease the pressure of the pneumatic tank, so you can change the power as well. This is a quick sample video of the jump shot. So for a dunking feature, right off the bat, we went for a perfect score for the dunking. So as you can see here, we have 3 tape measures, each go for different green tones in order to get the maximum points. What's unique about our design for our dunking feature is there's some other teams that use tape measures and stuff like that, but we are the only team, I believe, who has all 3 of our tape measures being pulled by one motor. And we did that, we did a gear chain down here with one motor that attaches to a dowel, and that dowel is attached to all 3 of these yellow strings. We pulled the strings down and then extended out. And that has allowed us to use our other motor as a way, it is attached to all these black strings as a way to activate the release mechanism. And here's an example of all of our tape measures extended, as you can see over here, to go before all 3 strings.
Literally, our design here is rapidly manufactured and rapidly installed. We only offer some items that involve with measuring tape, string, and paper as well. Our final cost is $55.04, or the lowest given money. Any questions?
How's the reset of the tape measures?
Manual. So once it goes out, we have to roll up the tape measure vector. Yeah, we can do it within the 3 minutes. Yeah.
It's fairly intricate, but it doesn't take an unreasonable amount of
Yeah,
time.
a lot of practice, you get pretty quick at it.
Questions?
In your bill of materials, you only have one measuring tape, but I see 3.
We just cut it. It was
Yeah,
like
so we
50.
just cut it.
So measuring tapes can come in like 16 each and over.
Yeah. Yeah, and we like take, we stick, so we would cut them down to the length that we needed, and then we would just staple it to our, dowels to hold them in place.
Right.
Okay. So then, as I was looking at the picture of the 3 measuring tapes deployed, whatever the right word is, right? And you're using one motor, how did you adjust or account for the different places where the green cup is, right? The one green cup is in the middle and 2 are out, so how did you account for that?
So we changed this length of the string, and also, I don't know if you guys can see from here. So what we found is we have kind of like a spool that we've made here, and the difference of how far they were actually affected how far they've gone. So it's through trial and error, through adjusting those spools as well, on the lineup. So a lot of trial and error.
Great. Okay, good job, guys.
Thank you.
Thanks.
Thanks, everyone.
All right, so full force next.
Thank you. All right, so we'll have about 3 minutes presentation and then a couple minutes questions. And then you guys can go in there afterwards.
Okay. We need a robot here now, right?
Was that?
We need a robot in here now, right?
If you want to, yeah. If you want
We're
to.
gonna send robot.
Sure. If it starts raining, we might need to speak up. It's pretty loud.
Okay. Yes, just pretend I'm in the back of the
Is that usually where you sit the presentation? Like, far back?
No, back there.
And then you put on your headphones.
I'm not that
Are you on like hour 2 presentations?
Last 2. Yeah. All right, great.
Do we have to remove? That's in there.
It's fine.
No, we'll wait.
We thought we like weren't allowed in there, so we didn't have
Oh,
That was my fault, I told them that.
yeah,
They were listening to what I said.
there's no one there watching, so.
There we go.
it. All right, we're ready now.
All right, whenever y'all are ready.
All right, good evening, y'all. This is our final project design review, and we're a team built different, A44. We have Atticus Cohen, Quinn Q, which is I, and Brooke Waller over there. So here's our design, and as a team, we decided we want to make it extremely compact, as you can see. When compared to the other robots, it's a lot smaller. We thought that's what made it unique. We also added lights on the bottom for aesthetic reasons. And what also stands out is we have these buttons right here, which are labeled for start button, this and this button, wheel up and down, the dunking mechanism. So the dunking mechanism is a motor pulley system, which can be controlled by those buttons if you need to control it. And the jump shot is controlled by a pneumatic actuator. The ball holder is not on there right now because it's kind of fragile, but you get the gist. And here's the design evolution. So for design start 1, since it didn't need to run or move, we just had 2 pneumatic actuators which shot both into the dunk and the jump shot. And that's our final design, as you can see.
So we'll talk a little bit about our fabrication approach. So we use mostly laser cutting and 3D printing. So we laser cut our MDF. We kind of used inspiration from the original frame, but we changed it a bit, made it a little bit more clean. There's still a bit of adjustability, and then we 3D printed this piece here, which holds our 3 balls for jump, and then the 2 balls, as you can see up there, for our jump shot. And like we said, the 2 ball holder is a little bit fragile, so we actually have 2 of them as we can back up in case something happens. But we 3D printed the ball holder so that we could easily dump into the cups while holding the balls, and it just lowers down. And we also have gears that we've actually hidden. Most of the components of the internal are hidden that we cut out of MDF to run our motor robot.
So for completion effectiveness, there are 3 main things that a robot aims to do, which is launch, complete the jump shot, and dump. The launch is very consistent. We have the button on the front, and the code is going to run the same way every time, so that has 100% reliability and gives us 1 point. The jump shot, we aim to get 6 points by hitting the bucket with both balls. That happens about 90% of the time. Sometimes a ball will bounce into the cup, sometimes it'll bounce and go a different way. So that has 90% reliability, and then we expect 21 points for the dunk. It should drive up to the same spot every time and drop all 3 balls into the green cup, into one green cup. And that also has a 90% reliability based on if the wheel moves or something like that. In the future, we want to increase reliability. Maybe we adjust our drivetrain system or our pneumatic system to make the jump shot more reliable. Thank you.
Great. Just one question for me. So I'm still confused on how the red tube works. So how is it going to deposit the balls?
So basically, it's coded that once it gets to the cups, this will lower down for string here. It has tension in it right now, but
and then it's
start
I got
here,
it.
it will lower down. And then we have these controls in the front, which obviously aren't for the competition, but it made it really easy for us for setup. So we have control of kind of lowering this in and out. So we don't have to go in and wind up a string. It's very consistent and gives us a lot of control as we set up and makes the setup faster.
Thanks. Anybody else? Is it hard to access the interior? I didn't look on this side, so
No, this piece right
Oh,
here
right, okay,
actually
yeah,
slides right up, so we can get to everything.
Very cool. That's good. All right. Thanks. So feel free to wait in line or outside for reopening.
Okay,
We'll
thank
start
you.
right on the next team. 4-4, and then we got our last one here, 4-5. Yeah, you're welcome. All right, so we'll do 3 minutes of presentation, a couple minutes of question answer, and then we'll run your system afterwards. Okay.
We have some things to pass out.
Yeah. No bribing. So whenever you are.
Alrighty, you guys ready?
Yep.
Hello all, my name is Will Ciro.
I'm Noah Holloway.
My name is Shreya Chaudhary.
And I'm Kudran Mehta.
We are the Mechanical Monstars, and this is our robot, Mr. Slackhammer. Mr. Slackhammer is a simple, reliable, consistent design that's guaranteed to shoot jump shots over MJ and dunk all over Bugs Bunny. He's expected to score 38 points per trial.
First, I'll talk about the jump shot mechanism. So our jump shot is powered by a torsion spring that we got from the mousetraps provided. In order to increase reliability, we manufactured our own version of the mousetraps using laser cut MDF and brass wire. The mousetrap fires the catapult, which fires when a linear actuator releases, pushes the release latch out of the way. Our launch arm also consists of a custom-made 3D printed part, which holds the 2 ping pong balls. In terms of design evolution, in order to perfect our jump shot craft, we decreased the size of the launch arm and updated the guide rails and the latch mechanism to occupy less space within the robot frame.
Our jump shot is pretty consistent. In the first sprint, using a much rougher mousetrap design, we got both balls in 2 out of the 3 trials, and that got us 2nd overall in the jump shot category. And we're also expecting 16 points, and it also hit the target zone 100% of the time.
Next, I'll explain our dunk mechanism. Our dunk mechanism involves a streamlined approach to targeting the center green cup of the target zone. After Mr. Slackhammer attempts his jump shot, we then have equipped Mr. Slackhammer with a direct drive string, which is basically a laser coat wheel connected to one of the motors from our mechatronics kit. As he approaches the target zone, we use an IR sensor that stops the robot approximately 1.5 inches away from the first red cup. Next, we've created a customizable rack and pinion design that extends a drawer slide that approaches the center red cup, and a string that is latched, obviously to the top of the frame, tensions that pulls back the front of the cage and allows for all 3 bolts to drop into the cup.
Next, so with this design, we're looking at about 21 points, 6 for each ball, and 3 bonus points for getting it in the green cup. With a lot of testing, we're pretty confident in this design, and to make sure we don't disqualify ourselves, we implemented a kill switch timer that after 50 seconds stops all motion in the robot.
So what sets us, Mechanical Monstars, and Mr. Slackhammer apart? First and foremost is its repairability. As you can see from the parts we passed around, if something breaks during the competition, we can easily swap it out. And most of them are laser cut and easily produced. His simplicity is his greatest strength.
Things break, that's a fact of life. The truth is we're ready when things break with easily replaceable parts.
Coming from the simplicity, it gives consistent performance at a low cost, with the total cost coming in at just over $46. Furthermore, we're one of the only groups to utilize the mousetrap to directly power the jump shot mechanism.
Thank you for listening. With the Mechanical Monstars, we're ready to demolish the competition. Are there any questions?
Great. So the IR sensor is picking up on the front cup. Is that what it's picking up on?
That is correct.
Okay. It's pretty repeatable, or?
Yes, it has been consistent nearly 90% of the time.
Okay. Excellent.
The only problem we run into is if it turns, then it could pick up the side cup.
Okay.
But it's pretty consistent with picking up the first red cup.
Any other questions for the team? Good job. All right, so we'll see you out there in the robot ready.
Thank you so much.
All right.
That was a 4 or 5. Yeah. That was the last one.